Okay, hello twin. Meet again twin. This is going to be Taylor series 2, which is basically just using the Taylor series to like approximate functions, or if they have like these bound stuff, right? That's what they use it. So, or like find the bound of the error of the approximation. So whatever. All right. If it looks like this, use Taylor series. Okay. Um, so we're just gonna get started. So it says approximate the blah blah blah, blah to the x-ray of this, right? So we put this at fraction, so it's easy to look at. And then when it's this, right, you want to find the Taylor series or like the McLaren series or whatever, right? So in this case, if you look at the chart, nope, the chart thing right here, we don't have sine x squared, but we do have sine x, right? Which means you could use this right here to find out the series for this. But if you remember in the last video, we did already work that out in this problem right here. So I'm just gonna write it down. Just go rewatch the video if you forgot to do it. Like small brain. Okay. But that would be a little impressive if you did forget how to do it already. JK, doing. So according to this last thing we did, the Taylor series, or the McLaren series, actually I got my mic. Sorry for that. Hopefully I just bust your eardrums. So the McLaren series for this is going to be this. If I could write, that would be great actually. Right, and then as we found out from this lecture, the interval of convergence is just negative infinity to infinity, right? Right, so this is equal to this, right? So now we don't, this is like the whole point of using Taylor series is to make it like more manageable to deal with, right? So this, right, like this right here, is easier to manage than like sine x squared, right? So in this case, we can just plug this into the bound right there. So if you rewrite it, here I'll write it in red. So instead of sine x squared, we're gonna have just this right here. I forgot the summation thing, but just like pretend that's right there, okay? To use your imagination, because I don't feel like rewriting it. Okay, and then dx, right? Because it's interval, right? And then so we stop at the integral. Point here, when we're doing this stuff, you should only look at the x, because when we're dealing with interval bound stuff, so if it's in the interval and we're taking like we're taking the integral of it, right? Just deal with the x stuff. So we can rewrite this if it makes it easier to look at. Sorry, can rewrite it. Summation right here. I'll just rewrite it. Fuck. Okay, and then we have the non-x stuff, right? We just put it on the side right here. Times the n stuff. I mean the x stuff. Right. So then when we're taking the integral of this, it's gonna be easier to look at. I'm sorry here. Because like we don't have to take the interval of this. So if we write like this, we just rewrite it here, right? It stays the same. So but this changes, right? So then how do you deal with stuff when it looks like this? I'm gonna give you 2 seconds to think about it. 1, 2. Did you decide how we take the integral of this? We just add 1 to the power, right? And then divide it by the new power. So this new thing would be x to 4n plus 2 plus 1. You know, plus 1 right here. We're gonna do it, so it's gonna be over 3 divided by the new power, which is 4n plus 3, right? And take it from 1 to 0. Okay, so if we rewrite it, well, you know, if you rewrite it, if you do the bound stuff, right? So this is x, just like that, right? So it's that, and then whatever times 4n plus 3, right? Right. So whatever this is, it's always gonna be 1, and then minus the 0, but x is 0, right? So the whole thing should be 0. Okay. It doesn't matter what this power is. Doesn't matter what it's divided by. It's always gonna be 0. So you just ignore this part. And so now we have this times 1 over 4 and plus 3. So then our new equation is going to be summation of, so it's like this times 1, right? So I'll just write it. And then this times this. So we have 2n plus 1 factorial times 4n plus 3. Right, right? This is our like new equation that we're dealing with. But that's not what it's asking for, right? It's asking for the approximate the integral to an accuracy of 1 over 1,000, right? So which test could we use to apply to this? Okay, what does this look like right here? Okay, if you get this right, I'm gonna give you $2. No, I'm not. But like in theory, I would. Okay, 5, 4, 3, 2, 1. If you said alternating series, you would be partially correct because you know it's alternating thing, right? But we would be using the alternating series estimation theorem, so that's what we're gonna use. Just in case you don't remember what that is, it's basically we're allowed to use it because, well, it's alternating, right? That's like the condition, and then alternating series theorem is when we write it out, right? Like the whole, like all the terms, like n equals 0. Oh, that's a zesty 0. n equals 1, n equals 2, until we get to when it's bigger than 1 over 1,000. So, right, this is what we're looking for. So we just write it term by term until we get what we're looking for. So, well, this is a equation, right? So we're plugging 0. I'll write it so you don't get confused. This is what we're using for this, not this. So, n equals 0, right? So, minus 1 is 0, that's just 1, right? 1 times 1, that's 1. Perfect. And then 2n plus 1 factorial, so that's 0, right? So 2 times 3, that's 0, plus 1, that's 1 factorial, times 0 plus 3, that's just 3. Okay, next one, negative 1 to the first power is negative 1, so this is going to be minus 1 over 2 plus 1, that's going to be 3 factorial times 4 plus 3, 7, right? And then as you're doing it, you can, you should simplify it so you can see if it's over 1,000. So 3 factorial, that's going to be 3 times 2 times 1, so that's going to be 6 times 7, so that, fuck you. Don't make a fucking 6-7 joke, I just realized that, bro. Oh my goodness, bro, you ailed me. I already know that stupid shit you're gonna say, bro. Don't even text me about it. Don't even comment, don't watch my videos anymore, actually. Don't, I need you. Sorry. So this number times that number is going to equal negative 1 over 42. Sorry, mine didn't crash out. This one factorial is just 1, right? So we have 1 over 3 here. So this one's not over 1,000 yet, so we keep going. So plug in n equals 2, so in this case, well, negative 1 to the second power is positive, so then we have 1 over, that's 4 plus 1, so we have 5 factorial times, well, it's 8 plus 3, so it's 11, so that's a big number, so we can kind of probably work that out, right? So we have 1 over 5 factorial, so that's factorials, right? It's like everything under it, so it's 5 times 4 times 3 times 2, that's 1, so 5 times 4, that's 20, 2 times 3, right over here. Wow, this is SD thing. So that's 120, so we have 120 times 11, and that's a big ass number. You don't have to simplify this one because we know that's going to be 1 over 1,000. Unless he asks you for the bound when it's over, but then they're not. So this is all going to be, this over 1 is smaller than 1 over 1,000, right? So that means that's going to be our stopping point, and we're only going to be looking at these two terms right here. And then note, if it's like small numbers like these, if it's manageable, you should simplify into one term. So usually you could leave it like this, but in this case, since it's small enough, we can simplify it. So to get 42, get common denominators, right? So it's going to be 13 over 42. That's 1 over 42, so that's going to be equal to, no, it's going to be 14 over 32. I just lied to you. Right, because 42 divided by 3 is this. Yeah, I'm smart, for real. So this is your answer. Can you read that as a 13? 13 over 42, and that would be your answer. Here, I'll let you look at it. I can't really fit everything on screen. Might pause the video, twin. I know you're going to need it, twin. JK. Right. Easy enough. Oh yeah, I should also say that after we get like this first series and we're going to the second part right here when we're looking for the error, there's two like different like theorems we could use. We could use the estimation, alternating series estimation, the ASCII, or we can use what we're gonna learn later, which is Taylor's remainder estimation theorem, which is also TRET, whatever you want to call it. So this is the two theorems we use. So alternating, like you use it when it's alternating. If it's not alternating, you can't use it to use the other one. Basic shit, bro. Get it in your stupid fucking head. I'm sorry, I didn't mean that. One. Okay. Next problem. So, look at this. Well, we don't have a Maclaurin series for this, right? But we do have a Maclaurin series for cosine x, right? So, you can use that for this. So, let's write it out. So when it's cosine x, it's going to be I think. Did I write that correctly? Yeah, I did. Okay. And this is... Okay. So, well, easy enough, right? This is also x1 half. So if we plug it in, plugging it to right here, our new x is just x to the 1/2, right? So just x. So we rewrite this. So now we have x. Or I guess we could, 1/2 times 2n. Here, so looking at it, you see that these two cancel, right? So you can rewrite it as, oh, I changed colors. Guess we're writing it right now. So now it's just going to be x to the n power. Right, so this is our new series, and then, but that's not like the answer, right, because we're looking for the interval, or approximate the intervals, right, so we gotta plug it into the interval. Beautiful, wow. So we plug this into it, right, and then, if you remember what I said, we're just looking at the x of the thing, so to make it easier to look at, you could just put the other shit to the side, and then times the x and dx, so this way, we're just focusing on this part. That's an x. Yeah, so we're just focusing on this part when we're taking the interval, so the interval, I forgot the summation again, it's okay. I'm not testing right now, so no, it's going to take points off. So this stays the same, right? But this changes to an interval where you just plus 1 to the degree divided by the new degree. So in this case, x n plus 1 divided by n plus 1. And then our bounds are 1 to 0. And like the other one, if we plug in 1, right? 1 plus 1 over n plus 1, right? And then minus 0. Right? But it doesn't matter whatever this is, because this is just going to equal 0, and then this top part right here is just going to equal to 1, right? So if we rewrite it, we got this part right here. Whoa, I did not mean to do that. Factorial, so this part times 1, so I'm just going to leave like this, and then times the bottom part, so n plus 1. So perfect. So this is our new series that we are working with, and then we gotta approximate it to this, right? So this is also 1 over. This is like too much to look at right there. So like this problem right here, we use because it's alternating, right? So we're allowed to use the alternating series estimation thing. So we just start with n equals 0, n equals 1, n equals 2, and then we just plug it in. So in this case, so plug in n equals 0, that's just 1. So 1 on top, 2, so we got 0 factorial times, and 0 plus 1 is just 1, okay? So we know that's not going to be smaller than this, right? So we keep going. Next one, well, that's going to be negative, so we did that, 2n, so 2 times 1, so that's just 2 factorial. I can just write it like this, actually, 2 factorial times 1 plus 1, that's just 2. Next one, this is positive. Alright, so this doesn't look like it's going to be less than 1 over 1,000, so we got to keep going, unfortunately. But you can like simplify it out as you go along to make sure. So next one, n equals 3, so it's going to be negative. Sorry, I'm tweeting a little bit because one of my favorite songs is on. Sorry, getting distracted by heat right now in my ears. And then that's going to be 4. So this one looks kind of big, right? Right, so we can simplify this. So 6 times 5 times 4 times 3 times 2 times 1, right? And that's going to be, fuck, so that's 30. Okay, so this is going to be 1,720 times 4. Use your brain, it's going to be less than 1 over 1,000, so this is, we know to stop there, right? So these are the 3 terms we're going to be looking at. 0 factorial, that's just 1, right? So 1 has 1 over 1, or I guess, whatever, it's going to be 1. Minus 1 over 2 factorial times 2. 2 factorial is just 2, right? So that's 2 times 2 on the bottom, right here. Plus this, right? So we have 4 times 3 times 2, which is 12 times 2, which is 24, right, for the factorial. So we got 24 times 3, and that's going to be 72. So this is our answer right here. Yippee! I don't think you need to simplify it. I think it's just fine if you leave it like this. So that's going to be the approximate. So easy. Here, you can look at it. I think it's most of it. Okay, pause the video if you need to win. It's definitely not a water break for me. Okay, next one. This is a bunch of gap. You probably read this. Here, I'll let you pause it if you want to read it. But basically, this is going to be the next theorem. And I think you do have to memorize these this equation right here. So you want to remember this one and then this one right here. So the remainder. So we have mxa n. Okay, right? So n is just like the number, right? Like the degree or whatever. A center, x, and then new thing m is what we're going to be like looking for most of the times, and then r is the remainder. So these are like the values we are going to be looking for, like the questions. So like here we can just do like the examples. So read the question, right? Use the Taylor remainder estimation theory to find an upper bound of the error of using the second degree Maclaurin approximation of e to the x to approximate. Is that what I said? To approximate square root of e. So immediately, Maclaurin, second degree, and then this stuff, right? So what does this mean? Well, Maclaurin means a equals 0, right? Degree is going to mean n equals 2, and then this case, right? We have ex, and then we want it where we have e to the x, but we don't have square root of e, right? But this can also be rewritten like that, right? The square root of e. So then if we compare it, it's already in like the e format, so then thus x is equal to 1/2. So checking off the box, sorry, we have n, we have a, we have x, but we do not have m, right? This is m right here. It's like, what the fuck is that, right? So that means that we have to look for m. So that's going to be our first first step, right? So rewrite the equation, right? Let n plus 1. and we're looking for m, right? Okay, so fn plus 1, that's an n, I don't know if you can tell. So we know n is 2, so 2 plus 1 equals 3, and then c is a constant, and then m, well in this case, because it says use the approximation of this, right? So we're going to use this, that's close enough. Like that, right? So, c in this case would be using this, right? So it's going to be e to the 1/2. And I should have clarified this before, but e is a special case because it's not a number, right? E, it's like kind of like pi, it's like a forever number, right? So it's not a specific value. So in that case, e or like m in this case is like unique, right? So like in this case, m could be 3, m could be 4, because you look it up on Google. Yeah, I can look it up right now. No, I won't. But e is like 2 point something, 2.7, something, right? So we can use a number bigger than that to approximate. So in this case, we can use a 3. So this is, instead of e of 1/2, we do 3 of 1/2. Is equal to m, because if we just leave it like this, well, what are we going to do with it, right? We can't, e is not a value, we can't do anything more with it. So we're going to put it in terms of, like what's that called, like a direct number or something, or whatever. So this is going to be our m. So now that we have all of our variables, we can plug it into the thing. So remainder n, which is 2, and then x, which is 1/2. So m, 3, 1/2, times x, which is 1/2 minus a, which is 0, to the n plus 1. So that's going to be 3. And then n plus 1 factorial, which is 2 plus 1 factorial, which is going to be 3 factorial. Simplify this even more, right? You can also write that as that. 2, that's a 3. I don't know if you can see that. I'll just put it on the outside. So then if you do 1/2 times 1/2 times 1/2, you're going to get square root of 3 times 3 factorial times, and I believe that's going to be 2 times 2 is 4. 4 times 2. 4 times 2, that's 8. And then 3 factorial is 6, because 3 times 2 is 1. So then this can also be equal to square root of 3 over 48. And then this will be your answer, twin. Wow, look at that, right? So not bad, right? This next question, yeah, you see, e is less than 3. It's just telling you that using, instead of using the e, just replace with 3. I'm pretty sure 4 also works, but like it's going to be like a different, like a less accurate approximation, right? Because it's further away from the value. I'll quickly do this one, I think, and then I think I could just stop here, because this is like the same bullshit. This is just like comparing the two. But I think you'll be fine. I'll just do this last one, because this one's like easy, I think. So the question says, what is the upper bound of the error using the third degree Maclaurin approximation of e to the x approximate? Actually, you can do this one by yourself. I believe in you. Do this one by yourself. The answer is 6. If you want me to go through it, I'll go through it, but the answer for this one is 6. Whoa, can you read that 6? I'll do this one, because this one's e to the power, so it's the same process as this, but I'll do this one because it's sine 1, and it's different, so you can see it, right? So this one's asking us, using the third degree, I'm going to use yellow, I'm in a yellow mood. Third degree, Maclaurin, sine 1. Using 2 ways, alternating string, summation theorem, and then the Taylor remainder. So using AC and Tret, okay? So, well, looking at the thing, what actually we don't need this for the first one, so I won't say it. Okay. So sine 1, right? So that's basically like sine x, right? Ooh, I should probably erase this. So that's basically like this, right? So we could just use this. Let's see if I remember it. Yeah. B. So, twin. Okay, hi twin. There's a cut in the video. That's because I accidentally stopped recording. It's not because I was tweaking. I forgot to do this. Okay, trust. So let's read the question. Calculate the upper bound of the error using the third degree Maclaurin approximation of sine 1 in 2 ways. So using the alternating series theorem, and then Tret. So we're gonna use AC and Tret. So first one, alternating series test, right? So it's sine 1, right? So we don't have sine 1 for sine x, so we just copy this, right? And then this test is when you just write it all out, right? So, and it says third degree, right? So third degree is like the third term. So this is first term, and then second term, and then third term. Like don't let it confuse you that it's n equals 0, n equals 1, n equals 2. This is first term, second term, third term, right? So just like a little FYI. So let's plug in 0 to this, right? This is 1 times 1 is gonna be x, and then this is 0 plus 1 is 1 power over 0 plus 1, so that's 1 factorial. Next one minus 1 over, no it's not, it's x. That's ugly. X, and then minus this 3, and then this is 3 factorial, and then this one is going to be plugging it into, right? Plugging this. Right, so this is for sine x, right? And we have sine 1, so easy like change, right? We just replace x with 5. I mean, x with 1. Well, I'm tweaking out. Sorry. And then the equation, or the question says using the third degree, right? So we're only using this term right here, only using the third degree. So we could just ignore these two. If it was asking like this question, no, if it was asking like this question right here, like approximate, then we would be using that one inside of the line. In this case, it's asking us to use the third degree. So in this case, this is the third degree. It's the fifth to 5 factorial. And then we plug in the 1, so we have 1 to the 5th power, which is just 1, and then 5 factorial, right? So then 5 times 4 times 1, right? That's going to be whatever, 120. So using AC, that's going to be our answer, which is great, right? And then that's the first part, and the second part is using tread. So we're looking at our thing, right? Third degree means n equals 3. Maclaurin means a equals 0. And then sine 1, like what we said right here, so that means x is going to equal to 1. So like this equation up here, we're just missing m. So we gotta look for m. So according to this equation right here that you will have memorized, right? Right, Turn? You have it memorized already? Yeah, I knew it. I know you have it memorized. I'll give you a second to think about it, so you can like get in your head. But, I'll write by treads right here. So we have n plus 1. So n plus 1 for the thing, n is 3, so this one's going to be 4. And then of c, of m. In this case, our m is sine c, right? Because it's going to be like this. We don't know what x is. Right. Sine, we have a sine 1 of 1 is this 1, right? If I'm looking at the unit circle. I think so. So this is going to be 1. If you use the unit circle, right? Sine of 1 is 1. So then this is going to be our new m. Maybe I should do yellow. This is green. Wow, that's ugly. Never mind. No highlighter for you. So that's our new m. So then we plug into the thing. So we got remainder and our n is 3. Sorry, we're using this equation right here that you will have memorized. And x in this case is 1. So then we have m, which is 1, times x minus a, and then x is 1 minus a, so that's a 0. And then n plus 1 up here, so that's 3 plus 1, which is 4, divided by n plus 1 factorial, which is 4 factorial. So 1 times 1 to the 4th power, that's 1, right? And then 4 factorial, so then this is 1 over 24. So that's our answer. Ooh, it's green. Which gives a better error bound. Well, use your chemistry little brain. Which one is bigger? I mean, which one's better? I'll give you 3 seconds to decide. 3, 2, 1. If you said this first one, you would be correct, right? The smaller the error, the better. So, yep. Pretty easy. This is just showing you that if you use the AC method, it's going to be more accurate. But if they tell you to use tread, like, womp womp, basically. That's going to be it, twin. Basically, what you do is, you do the thing, right? So we do n equals. This is third degree. Third degree, what does that mean? No, I know what that means, bro. Am I tweaking out? Okay, I'm gonna try this, and then if it's wrong, I'm gonna cry and cut this out so you never see it. So okay, so wait, this one's. Oh wait, I have to see this one. No, I'm cutting this shit out. What the hell am I looking at?